Chapter 18, Electric Forces and Electric Field. Now, both of these concepts are really important, and we'll see that electric forces are really closely tied to our idea called the electric field. But before we get into either of those, we first want to talk about what makes up something electric, what makes up electricity. So that's what our first section is. Our first section is the origin of electricity, section 18.1. It turns out the electrical nature of matter, of everything we know, is inherent in atomic structure. So if you look at an atom, we know that it's made up of protons and neutrons in the center, and then there's electrons that are in a cloud flying around, and we know the mass of each of those very precisely, right? So the mass of the proton, 1.673 times 10 to the minus 27 kilograms. The mass of the neutron is very similar to that of the proton. It's almost identical, 1.675 times 10 to the minus 27 kilograms. So they're about the same size. In contrast, the electron is tiny, right? Mass of the electron, 9.11, which initially sounds big, and then you look at the power of 10, 10 to the minus 31. So it's about 10 to the 4, 10 to the 3 or 4, so 1,000 to 10,000 times smaller than a proton. The electron is tiny, tiny, tiny. All of these really are tiny. But each of these also has an inherent charge to it, right? We know that protons have positive charge, neutrons have no charge, which is why they're shown with no symbol there, and the electrons have a negative charge. And interestingly, even though the masses are so different, protons and electrons have the same magnitude of charge. And that's given by this constant E. So we can note that this will be the charge of a single electron or that of a proton, at least in magnitude. So the charge of an electron or a proton, knowing that the electron will have to be negative, that's something you'll often have to fill in. But in magnitude, it's given by 1.60 times 10 to the minus 19 C, where this capital C is a unit known as the Coulomb, in honor of the scientist with the last name Coulomb, who described the electric force, which we'll be getting to in just a little bit. That is Coulomb's law. But this is the first thing that we really want to take away. The masses are also useful, but there's something you can also look up as needed. We're really focused on the electric charge, how much charge is present. So we want to hold on to that. And in nature, atoms are normally found with equal numbers of protons and electrons. So as long as you have an equal number of them, they have the same magnitude of charge, and so they're electrically neutral. They're stable, right? We notice in this picture, there are 4 electrons, and sure enough, there are 4 protons. And so it balances out to 0 net charge, right? Notice there are even 5 neutrons in here, and that doesn't make any difference because the neutron's neutral. Now we can get a net charge if we add or remove electrons from a material. The electrons are the ones that are always going to move because they're flying around and they're loose. So they're the ones that are able to, versus the protons are held, they're fixed in the center of that nucleus. So if we add or remove electrons, we can have an atom with a net electric charge. And that net electric charge is equal to E, the fundamental charge, times the number of electrons that are added or removed, which we can note with a capital N. So the Q here is going to be our general symbol for charge. So how much charge something has, because usually it has more than 1 net electron. And then N is just the number of electrons, and E is that fundamental charge as mentioned before. So now that we have this basic understanding, let's try to get a better sense of how that number of electrons will correspond to the total amount of charge. So let's look at an example of this. So example 1, a lot of electrons. How many electrons are there in 1 Coulomb of negative charge? Well, one answer is already given for you, right? It's a lot. But just how much is it? Well, that's where we can investigate. Let's figure out first, what do we know here? What are we looking for? Well, it mentions this 1 coulomb of negative charge. So what is that telling us? Well, that's giving us 1c, and that's going to be our Q, right? The amount of charge that we have. What are we trying to solve for? We're trying to solve for how many electrons. So that's going to correspond to our capital N. And the key here is that it's asking about electrons. So because it's asking about electrons, we know that fundamental charge of an electron, E, is 1.60 times 10 to the negative 19. C. Right, so hopefully now you see what we might want to do here, right? If we think of that equation that we just got, Q is equal to N times E, then we can solve for our N, because that is what we're ultimately looking for. So if we divide E to the other side, so we take our total charge Q and make that 1 coulomb, divide by E, 1.60 times 10 to the minus 19 C, we come out with 6.25 times 10 to the 18. With what units? Well, notice the coulombs cancel out. And that's because we just solved for a number of electrons. So it doesn't really have units, though you could write electrons here, because that would tell you how many, this is saying how many electrons there are in just 1 coulomb of charge. It doesn't sound like that much, but that is a lot of electrons. 6.25 times 10 to the positive 18. So that hopefully gives you some sense. We're going to generally be talking about a lot of electrons, but we won't necessarily focus on all the individual ones that make things up. We'll just say that there is some amount of total charge, and we know that we could break it down to the electron level if we so chose. All right, so this introduces the origin of electricity.